Hey all, if you're like me, you might have designed a CAD part or piece that you want to have manufactured into an actual physical part that you can use for, say, a fuselage for an aircraft or some other piece. And there's a few ways you might usually do this. You might 3D print it, where you put the STL through a slicer and generate the G code for a machine to use. Or you might, say, go ahead and make a mold so that you can make a composite piece out of it like this, but that comes along with its own challenges. The geometry might be too complex to do without vacuum bagging or some other form fitting technique to get the contours into the composites. So what else can you do? Say you don't have a router or CNC mill to turn this into a plug that you can use to form the geometry from the outside. But say you do have a CNC wire cutter that you could use to cut the geometry out of foam. Unfortunately, with the current state of uh, commercial or open source uh, wire cutter slicers, it'd be pretty difficult to turn this geometry into something you can cut without going through a lot of manual steps. Something you could do to get it started piece by piece is you could say put in planes to the CAD geometry and then get the intersection, and here you have a nice contour that you can use. But then you have to generate 20, 40, 50 of these to get the actual cross sections that you use to cut the shape with your wire cutter. Now these you could save as DAT files or DXFs and you can import them into Jetty Or say you're using something like DevFuseFoam where you can have the cross sections, you can have each planar view of the shape imported into DevFuseFoam and you go one by one and you draw the cross sections for every piece you want to make. But then another issue with DevFuseFoam is it doesn't let you split up those cross sections. So you end up having a lot of wasted material. Say something like this, where all the internal space ends up being wasted foam that you may or not be able to use with another piece that you have planned. But a lot of times this would just be scrap material that you end up throwing away. Or you can section it out on a larger piece, so you have a lot of pieces being cut out of a single sheet of foam, but you still have the internal pockets that may or may not be used for something else due to the fact that they're not a contiguous piece. So I decided, why don't I just write my own slicer for CNC wire cutters? I have experience with Python and Java and other programming languages from college and work, and I decided, well, I might as well just go with Python because they have nice libraries that other slicers use, such as Cura. You can import TriMesh, and TriMesh is used for handling STLs in a lot of places, especially for getting cross sections for slicing. So I started working on this a few months ago, and the general idea was that you import your STL, it subdivides the entire domain into a bunch of cross sections based on the size of your workpiece, the foam that you're going to be cutting the pieces out of, and the direction that you want the cross sections to be normal to. If the geometry has holes in it, say it's hollow, then it just converts those cross sections directly to uh, cross section pairs where each cross section is duplicated in the centers. That way they mesh up properly. Or say the part isn't hollow, it's a solid piece, then you could specify a wall thickness and it would make the pieces hollow, all the cross sections hollow. And the reason you want it hollow is so that we can subdivide that cross section into a bunch of smaller pieces that don't take up as much total area because the internal hole no longer is a hole. It's another exterior part on the opposite side. So once you subdivide all these pieces into, say, four new cross sections per the global cross section. So instead of, say, 50 cross sections, now you might have 200. But these 200 don't take up a whole circle with a large hollow space in the middle. So now you can position these smaller cross sections in a more optimal layout to better use the entire workpiece. Say a circle becomes just 4 arcs, well, those 4 arcs can be stacked on top of each other. In a way, they take up a lot less area on the total workpiece than if you just had the full circle, taking up the entire internal space that you're going to end up scrapping because you don't have a use for it anymore. And then once you have this positioning for all the smaller cross sections, you convert it into a cut path, and that cut path is converted into a tool path. And then once you have the tool path that each gantry follows, you just turn those movement commands into G-code. And so that's what I started working on. But while I was at it, I decided that I'd also implement wings. That way I wouldn't need to keep using JettyCut. I could just completely use this tool. Now, currently, the tool is not even through command line. I just run it through PyCharm or idle through the interfacing window. I just have a tester script that I run everything with. But the end goal would be to have all the features supported by command line input and then write a GUI that goes over the top of it. That way users don't have to interface with command line. So next I'll be showing some of the steps along the way to where I'm currently at now and what I have left still to do to get to the part where I wanted to be at, and then any additional features or things I plan on adding. But yeah, thanks for watching. So when I started on this, I first started on doing the wings portion because I assumed that would be the easiest and the best part to start testing on. And what I quickly found out is that DAT files from databases like airfoiltools.com aren't necessarily always sorted in the same order due to the fact that there's multiple formats for DAT files. So the first order of business was to implement a sorting algorithm to sort points into a clockwise order. Now my first naive approach was to try ray tracing. This worked in most cases, but it was extremely inefficient and slow, and I realized that I already knew where all the points were, so there's no point in trying ray tracing. My second approach was converting everything to polar coordinates and then just sorting by theta, and this also worked pretty well in most cases except for when the airfoil was extremely cambered and you ended up intersecting lines, and that ended up causing a lot of back and forth between the cambered section around the trailing edge and just jumping back and forth on points. So my third approach was just trying to use a weighted distance method to sort the points. Now this was a weighted distance between x and y coordinates, with x being weighted a lot more, and then also weighted with the angle from one point to the next relative to the previous angle to get to the point you're currently at. And this worked better for most cases until I started testing it on extremely thin or highly cambered airfoils. So then I ended up coming to the fourth method, which is a little bit more of a complex polar sorting method. In this method, I subdivide the domain into a bunch of central lines through the cross section. These central lines define top and bottom. That way I don't transition from the top to the bottom too early, which is one of the issues I had with highly cambered or thin airfoils. It would suddenly transition from the top to the bottom. But along with this, I also do a polar sweep from top to right and from bottom to left, and that way whichever point I encounter first, I check within some tolerance. That way you can end up grabbing multiple points, and then out of the multiple points I grab the closest one. This allows it to get a pretty good clockwise sorting for the airfoil on the top and the bottom side. So then I moved on to doing toolpaths. Toolpaths themselves aren't too difficult. All it takes is having the two sections you're cutting, and then out of all those points you line up the points in whatever manner you want to produce a proper loft, and then you form a line between those 2 points and extrapolate out to where the gantries are. And then this gives you the motion that the gantry needs to follow for the line to pass through those 2 points at any given time. Now, the real difficult part of this is forming the two cutting sections and getting them to line up in a way that produces a proper loft. And that's part of what sorting was meant to do, is sort them in a way that you get a proper lofting shape. So this was my first test cut. I think I was cutting an AG35 airfoil, which is a pretty thin airfoil, and I was just doing it out of scrap, pretty bad piece of packing foam I usually don't use for actual parts. So overall, the cut wasn't too bad on the forward section of the wing, but when it got to the trailing edge, the way it looped around and the way it was cutting wasn't very good for actually maintaining the trailing edge. So at this point, I realized that I needed to probably re-architecture a lot of the code that dealt with going from cross sections to actual toolpaths. So I ended up implementing a step in between, which I just called cut path in the software. And so you end up forming a cut path, and then the cut path goes directly into a tool path. Now, there are some pretty interesting bugs that I encountered along the way whenever I started changing the way the software worked. And some of these are pretty interesting, especially if you try cutting them out in 3D space. You end up getting some pretty interesting parts. While not very useful, they're at least pretty interesting to look at. So here's the first proper cut after getting all the cut path to tool path code working. And I ended up structuring cut paths in a way that you build up section after section in a way that they all connect together. And that way it's a bit more of an abstract way of forming the actual cut you want to do. And I ended up architecturing it this way. That way whenever you get to the multiple subdivided cross sections, you just sort of add them together in a linear path to get the actual cut profile. So the next part to work on that's required for hollowing out cross sections and also compensating for the wire burning or kerf was to implement parallel curves. Uh, and this was pretty interesting because of some of the bugs that came out of it. Produce pretty interesting shapes, but it's pretty simple. You calculate the normal vector at each point, and then you adjust out or in from that normal vector by whatever your offset amount is. Now, the difficult part with this is removing intersections. Um, I didn't really, I did calculate intersections and tried to remove them piece by piece, but that ended up being pretty slow. So I just went with another method that ends up culling any points that are within the offset distance to the original path. And if they're within the offset, that means that they're not actually the full offset away, so you can safely cull them and just reform the shape out of the points that remain. So at this point, I ended up implementing a feature that I wish JettyCut had, and that was allowing you to transform the actual cut section in 3D space. That way you can align and adjust for a sweep. So in highly swept wings, you can rotate it so that it doesn't end up pulling the gantries as far apart as you'd end up doing if you just kept the sweep in. And then at this point, I also started incorporating the offset or parallel curves into kerf compensation. So when you do the kerf compensation, you want to adjust for the wire actually burning through the material of the foam. And I've been trying to do this in a dynamic way where you set the kerf for the machine and then that's the reference for the larger section path, and then the smaller section path is dynamically adjusted by the taper ratio and some other constant factors. And before we get to the actual cross-section part of this, I wanted to show some of the interesting cuts you can end up with, especially if you don't well constrain the tool paths. So currently I'm constraining it so that if the leading edge ends up forming a extrapolation that ends up going below the x-axis, so into the negative quadrant, it will offset the entire cut path so that you don't end up receding past zero. Now the one thing I didn't end up constraining is that, say if the trailing edge forms a line that goes past that, I don't currently adjust for that, and that's what you see here. When I align the leading edge with the actual wire 0, ended up sweeping the trailing edge to the point where one of the gantry ends up needing to go backwards. And this could cause issues if you had the machine zeroed. It would end up just pounding against the end stop. But I offset the machine by 10 centimeters and started the cut to see how it actually turned out, because the actual tool path looks interesting. And it actually cut it pretty well. It's pretty interesting seeing one of the gantries actually go backwards and then the other gantry go almost all the way to the opposite end stop. And it's also a good test for the gravity tensioning system on my wire cutter. So now we get to the actual interesting part, and that's all the cross sections from STLs. To get to this point wasn't too difficult because TriMesh handles getting cross sections, although one thing TriMesh doesn't handle is enforcing the ordering of the points and also the spacing of the points, because I think it just grabs any edge that intersects with the plane, and then that edge becomes a new vertice, and based on how your STL is exported, that could be anywhere. So you end up having to sort the points. And then for the subdivision, well, at first it's a little bit janky. I just break the entire domain into polar quadrants, and then if the points are within that quadrant, I keep them. And so you end up getting each section. And then one issue with the sections now is that you end up losing some geometry, and that's because of the fact that the points could be anywhere in the geometry. I do add additional points prior to this step, but it doesn't always keep enough of them, and you can see in this part here that the section behind it actually recedes quite a bit, and that would result in a loft that's not desirable. But yeah, that's currently where I'm at. I still need to fix that geometry issue, and I'm just going to do that by inserting new points at the quadrant boundaries. And then here's the diagram from the start of the video, but color coded based on where I'm currently at. So things I still need to do is I don't currently check the STL if it's hollow, and I'm not even sure what the output would be if it is. I think currently try-mesh might crash because the function I'm calling, I think it's only valid if it is a solid geometry. So I still need to handle that whole section there. Currently I've just been testing with solid STLs and then making the inside hollow. And then after that, once I fix the subdivision issue, I need to transform them all in space and find a good algorithm for placing them. I'll probably just do like a Poisson distribution, uh, some sort of smoothing over a plane. And then after that, once I have all their positioning, I need to uh, implement a method to convert that into a cut path. Once I have the cut path, it's pretty easy going to a tool path, and I already have all the code in place for that. But there'll be added challenges of I need to add more constraints to make sure that you don't end up creating invalid tool paths that go outside of the machine range. So there might be some back and forth looping there, looking for an optimal placement that doesn't invalidate the wire cutter specifications. But yeah, that's currently where I'm at with the project. I have all the code up on GitHub and I'll put a link to it in the description. It's not super clean or pretty right now. I haven't been keeping track of filling out the doc strings and keeping track of all the general convention stuff like I would if I was at work. I've sort of just been working on this whenever I have time. But when it gets closer to a more completed state, I plan on generating some documentation for it before I go into creating the GUI. That way, if other people want to use it, uh, they should be able to pretty easily as long as the documentation's good. But yeah, thanks for watching everyone. Have a good day.